Welcome to the solar photovoltaic lecture. So both wind and solar have greatly increased over the past 20 years. We can see here in the blue, onshore wind started increasing in the 2000s, the early 2000s. And it wasn't until 2010 when we started to see larger increase in both small scale PV and more recently, larger increase in utility scale PV. We now see that we have over 1,000 gigawatts or a terawatt of wind and solar energy since 2018. Again, it's grown 65-fold since 2000, and it's more than quadrupled just in the last 10 years. If we can think in 2007, there was only 8 gigawatts of PV capacity installed compared to 89 gigawatts of wind. But since then, PV has grown from 8% to more than 46%, and it's actually expected to overtake, utility scale has already overtaken the small scale PV, and we actually expect it to overtake wind in the coming years. It estimates that, again, the first terawatt of wind and solar that was completed in 2018 required about 2.3 trillion of capital costs to deploy, but the second terawatt that's expected to come in the coming years will cost significantly less, if not half the cost of the first. If we look in Europe, the PV growth, even during this pandemic, we can see that in the first quarter and the second quarter that we saw increases in PV growth, residential PV growth compared to even 2019, with projected increases in the third quarter and the fourth quarter, especially in the 7 to 10 kilowatt range. Again, if we look at where the sun shines in terms of where solar PV should be installed, we can see here that we have the red being the highest kilowatt hours per meter squared, but we actually see our largest capacity here in China and in Europe, and as well as the United States. If we look specifically on the US, again, in the southwest of the US is where we have the largest annual solar kilowatt hours per meter squared, the highest levels. So in the US, our average system is around 5 kilowatts per hour, 5 kilowatts, excuse me. And so 5 kilowatt systems, the average cost as of August 2020 was a little less than $3 per watt, which means it's about a little less than $15,000 for a 5 kilowatt system. But after the federal discounts, as well as any local discounts could be even further than that, it's around $10,000 to build a typical system on a rooftop house in the US. But that price varies. Again, we can see different states. Here in Maryland, it's around $3 per watt, while in other places, New York, it's a little bit higher. Arizona, it's quite low. So again, it depends on where you live, and it depends on the electricity rate of that state. But if we see the cost per kilowatt hour, again, we're looking at where it used to be with over $3.60 and $3.70 almost in 2015. And again, in 5 years, we've already decreased to less than $3. So the amount of electricity that you get on your panel depends on many factors, including the direction and angle of your roof. You want the angle to match the longitude that you're at, as well as you want it to be south facing. But most importantly is how sunny it is. So a 5 kilowatt system in Vegas makes about 30% more electricity than one in Philly based on the amount of sun that they get. The average household in the US uses about 867 kilowatt hours a month, which is about 10,000 kilowatt hours per year. You can estimate for your location the PV output that you would get in any location in the US by using a tool by the National Renewable Energy Lab called PV Watts. So if you just Google pvlots.nler.gov, you can go to their website, and they have really great tools for estimating how much output you would get based on your location, based on the type of system that you buy. So if we look at some of these systems, we can see, for example, in Austin, Texas, we would get the average annual of about 7,000, which would be higher than New York, and the highest being in Phoenix, Arizona, based on the sun. But you can see that the cost of electricity is quite different for these areas. So for example, in New York, the cost of electricity is 18 cents per kilowatt hour, where it's much lower, for example, in St. Louis or in Seattle. And so what that does is why we have maybe higher solar radiation levels in a place like Memphis or even Topeka, or for example, Phoenix. And we have higher electricity use. So the production ratio, if we're using more electricity, we have more production. But what ends up happening is, even though New York has less sun, but it also has the highest electricity costs, you could actually save the most in New York. Because the cost of the system is fairly similar, but because you're offsetting a higher cost of electricity, you can actually have a lower payback period. Seattle's actually in the bottom of the list in terms of savings, again, because it doesn't have a lot of sun, but also it has very low electricity rates due to the large amount of hydropower in that state. So in sunnier states, the same panels will produce a lot more electricity than they would in other states. So Las Vegas, for example, would produce the most electricity, but it would only save about $730 per year. But that's actually less than New York, because they're offsetting 18 cents per kilowatt hours. Even though they're producing less, they're offsetting a higher cost rate. So if we look at PV cells are made based on photovoltaic materials that are semiconductors. So we're going to be concentrating on the semiconductors, which on your periodic table are the yellow elements. So when we look at silicon, so here's silicon. Silicon is a group 4 element semiconductor. And so it forms a diamond lattice, and it results in 4 valence electrons for each silicon atom. And we have crystalline silicon as well as amorphous silicon. And so what you can think of crystalline silicon means that the lattice is basically perfect, right? And so in PV, we're often using crystalline silicon, which is kind of the perfect, it's more expensive to manufacture, but it's that perfect lattice. And so it increases the efficiency when we use the silicon for our PV cells, as opposed to amorphous. It's a little bit cheaper cost, but our efficiency is going to go down because the structure of those valence is not perfect lattice structure. So it now goes to the swan of the perfect structure, the crystalline versus the duck. So again, when we're looking at this crystalline silicon, again, we have high efficiency rates. It's the established technology that we're using right now, and it's very stable. The disadvantages, it is a bit more expensive to produce. We need this lattice structure. It has a fairly low absorbance coefficient compared to some of the other elements that we may need to use, and it needs a lot of this purified silicon, but it is the industry leader in material that we use for PV panels. So again, how do PV panels work? They basically convert the sunlight directly into electricity by interactions of the photons in the sun and electrons within the semiconducting material. So silicon, which is our lattice structure, is doped with atoms from an element that have one more or one less electron than occurs in the matching substrate. For this example, it would be silicon. So a thin layer of each is formed a junction. The photons striking the cell cause this mismatched electron to dislodge, creating a current as it moves across this junction. And then these grids of connection, the current is gathered through a wire, and then it's used, the electrons are used. And again, various voltage and currents can be supplied by putting panels in series and parallel arrays of cells. So again, looking back at the silicon structure, silicon, again, it has those 4 electrons. So when these silicon atoms are brought together, each one forms a covalent bond with 4 silicon atoms in this tetrahedron geometry. So when we talk about our conductance band and our valence band, so here we have our conductance band and our valence band. So here if the valence band is full and the conductance band is empty, we have this energy gap. So we have electron energy and we have hole energy, and this is where we get our flow. So band theory is this existence of energy bands. And these energy bands are continuous ranges of energy with electrons which electrons may occupy, and gaps which they can't occupy. And so there's three types of material in band theory, which are differentiated by their electronic structure. So we have insulators, where we have this gap, where the gap is larger, so electrons are not really flowing through because the gaps is where they can't occupy. You have conductors where they flow very easily through. And then we have semiconductors, which is what we use in solar cells. And these solar cells have this band gap that we can cross in order to have our flow of electrons. So again, a semiconductor is of interest because their conductivity can be modulated by doping an impurity and offering a pathway to overcome this energy gap to control electronic circuits, versus an insulator with our empty band gap and a conductor which has a full valence. So when we look at the three types of semiconductors specifically that we have intrinsic semiconductor, we have an N-type and a P-type, okay? So these type 2 and 3 are the semiconductors that are gonna control the flow of electricity. How do they do that? By basically, the semiconductor has an impurity at that doping, and it carries the carriers placed in the conductance band or removed from the valence band. So basically, a photon enters from the sun and it's absorbed and lets the electron from the valence band get sent up to the conduction band. And therefore, a hole is left in this valence band, creating an absorption process where you have an electron and a hole pair. And that pair is what we get through the flow of electricity. So again, when we look at the intrinsic, it has the right number of electrons to fill the valence band. Therefore, the conductant band is empty. And because electrons in the full valence band can't move, this acts as an insulator. Once we have an N-type, the current is carried by negatively charged electrons. What we have is we look at group 5 impurity atoms. They're added to the silicon melt from which the crystal's grown. And so they have 4 out of 5 of their electrons used in the valence band. So then 1 of 5 is left to put in the conduction band. So these impurity are called the donors. So when within the conduction band, the electrons are moving, and therefore it becomes a conductor. So here so arsenic, for example, so here we have silicon, and here we have arsenic, which has this extra electron. So doping the silicon lattice with this group 5 element, such as arsenic, creates extra electrons in the conduction band, and that's a negative type carrier. So it's an N-type, and the arsenic becomes the electron donor. And then we have the P-type. So the P-type is current carried by the missing electron holes, which acts as these positively charged, again, electron hole pairs, and it acts as the positively charged particles. So a group 3 is added to the silicon melt. So they need 4 out of 5 electrons, but doping creates this lack of electrons in the valence band. So they're missing electrons. And so they're the holes that are used to carry the current through. So for example, a group 3 would be boron. And so doping with this group 3 element creates holes in the conduction band. So then these positive charge carriers, those are the P-type, and the boron becomes the acceptor. So what carries the current? So the prevailing charges are called the majority carriers. So the prevailing charge carrier in the N-type is the electron, and the prevailing charge carrier in the P-type are the holes. And so what we do is we put these p-n junctions together, okay? So the p-n junction is by combining the P-type and the N-type in very close contact to each other. And in this p-n junction, the current is only allowed to flow along the direction from the P-type to the N-type. And that's how we get our current that flows through. So again, you can see here we have the doping of electrons. And so we have a depletion layer, And so again, this is positively charged and negatively charged. So we have a reverse bias and a forward bias. And so the current flows from this p-type to this n-type. So again, when these two semiconductors come and transfer over to the p-type, we leave a positively charged area. So these holes from the p-type by interface transfer over to an n-type, leaving a negatively charged area. And because the electrons in the holes are swapped, the negative electrons become positive and the positive holes become negative, and a middle potential barrier with no charge due to the changing of charges is formed. So this potential barrier doesn't let any more electrons or holes flow through, and so this electric field pulls these electrons and holes into opposite directions and allow that current to flow from the p-n junction. So again, as a review, the photons are going to hit the solar cell. They're absorbed by the semiconducting material to create these electron-hole pairs. The electrons are knocked loose from their atoms, allowing them to flow through the material, through the p-n junction, and in which they produce from the p to the n, in which they produce electricity. So again, we're going to use semiconductor grade silicon, and then we're going to use trace materials. So for example, we might use boron as our 3, or phosphorus or arsenic or something else as our 5. We can use different materials. And so depending on the cost and the purity that you need, you might use different materials there. And then you have a metal base, and that metal base is the metallic contact that is going to then conduct the current so that we can use it. So again, this is in the book, there's a very good description of this different step between the p-n layer, the p-n junction, how the sun hits this p-n junction, and how we have our electric field that is formed. So again, you have these two silicon layers, phosphorus may be added to one, boron to the other, being the 3. And then we're going to put them together. It knocks it free, which are attracted to the positive charge. And then we attach wires from the p to the n layer, and the electrons flow through the wire. And then we add load so that we can use that current. Today's prevalent cell technologies are based on a single junction. So they only use one portion of the sun's energy spectrum. But we have emerging multi-junction cells that allow many layers to use progressive parts of the spectrum, which results in higher efficiency. So there's various means to create these layers that are actively being pursued. So again, our first was our single junction, which we've just described. It had a silicon and n-type and a p-type. Again, our contact, and then some sort of glass over it, and our electrode array, which again had the efficiency that was anywhere from 14 to 17%. And this was 99% of all of production back in 2013 when solar cells were starting to be produced. We also started to produce these second cell generations. These are these thin films. So these are the amorphous. So they're not the perfect crystalline structure, but actually we can bend them, we can put them in different configurations. And so thin film, they're less expensive compared to these first generation cells. And so then we're starting to use different doping agents, so cadmium and these different telluride, these different doping agents that helps us to expand the efficiency that we get from doping, but also have less costly material. So again, the efficiency in reality was more like 7 to 11%, but we demonstrated with a lower cost, we could get higher. But again, still right now, it's more of the single junction than the thin film that's being used in the industry. And then finally, we have the third generation, which is the multi-junction. So here with the multi-junction, you can see here, we have the spectrum. And so we take different parts of the spectrum, which is going to hit different parts of the cell. So it's going to have a top cell, a middle cell, and then your ordinary silicon cell. So the idea is if you just have the silicon cell, you may have that 13% efficiency. But then if you add these other cells, then your efficiency goes up because you're capturing more of the spectrum of the photons that are going through. And so these efficiencies are anywhere around 30%. So again, if we can get the cost of production higher and we can produce more of these cells, then again, our efficiency would be much greater with the same photon that's coming through no matter where we are in the world. And so again, these are some tandem cells, which is the same thing, this idea that we have this blue cell, depending on the spectrum of light that we're seeing here. So we're gonna get some of the blue cell, then the green cell, and the red cell. And so the idea is that it comes through, so the top cell is gonna have the large band gap, and then a middle band gap, and then a small band gap, so that we can get the whole array of light that's coming through each photon that strikes the plate. So when we look at the solar cell production process, so again, we have our sand, which is silicon. And so we're going to basically cook this sand. And so then we're gonna take this, this furnace, that's coke reduction, that's left over, dissolve it, we're gonna distill it. Again, we're gonna heat it into these crystalline structures, and then we're gonna use diamond sawing to basically create these really nice wafers. We're gonna polish the wafers. We're gonna again dope them to do the p-n junction, have an anti-reflection coating, and then we're going to interconnect and encapsulate this into modules. And then finally, we're going to test them to make sure that we're getting the efficiency that we expect. So our solar cells is a DC current. So DC flows in one direction. And so it's a direct current. And so if we have batteries, batteries are also direct currents. Now, if we are in the US, we use alternating current. So we actually have reverses its flow at regular intervals. So this is direct current, the electrons going through a cell. This is our alternating current. And so we use alternating current because we have less, over long distances, your alternating current loses less energy compared to direct current. So in the US, we change it to alternating current. So we must convert them from DC to AC using an inverter in order to use them if we're not running them onto a battery and then using the battery. So if we look again at our installed capacity, so if we look, this is specifically just for the US now. Again, we can see from 2009 to 2017, we've grown in the megawatts of direct current, so 55,000 megawatts of direct current that we've seen over the last 10 years. And if we see in the world production, again, China leads the way with 131 gigawatts, and then there's a huge jump down to the US, Japan, Germany, and then Italy, India, United Kingdom, France, Australia. But you can see many of these are actually fairly colder weather climates compared to India and Australia, which have more sunshine. If we look specifically for the US, in the US, California by far has the most solar capacity than any other state in terms of megawatt capacity, followed by actually North Carolina, Arizona, New Jersey, Massachusetts, Texas, Utah, Georgia. And so again, the annual capacity additions is also growing in these same states. If we look at where these solar cells are manufactured though, most of them are manufactured in China, with Taiwan, Japan, South Korea, India, and the US being others. Again, if we look at the monojunction, this used to be 90% of the market. It is now less than 25% of the market, with most of them now being the multi-junction silicon cells, but still using silicon instead of cadmium as the base. And then again, if we look at different manufacturers, there's really so many manufacturers. So others 63%, with Trina Solar out of Europe being one of the bigger ones. And then we have quite a few out of China, as well as Japan, that are leading the marketplace. And that is the end of our solar PV lecture. I hope this helped you learn how electricity is made using a PV cell.